project I've been working on for maybe the past couple months. I guess I don't know as much as a lot of people when coming to KansasFest, but I've been studying this pretty recently and just studying the Apple IIgs and how things work internally, because there's a lot of good books about how the Apple II 8-bit machines work, like anything like say real detailed analysis. And then we get to the IIgs, and you have quite a few custom chips that either they didn't want to release documentation or they just didn't get around to it by that time.
Just didn't want to release it.
Yeah, there is like a trend. I know the older Apple IIs told you everything. The Macintosh told you nothing, and if you read the Apple IIgs manuals, they're kind of like in the middle. They say, don't do this, but if you want to do this, here's how. And so there is some information, but definitely on central timing issues, they don't have any information about that. So I basically hooked up a lot of analyzers to a ROM 3, took some traces, and either verified stuff that was in manuals or found out some new stuff. So this is where I'm today. Specifically, in the chip I'm working on right now, the FPI, is called Fast Processor Interface, or ROM 1. And ROM 3GS, they call it Control Your Apple, which I have no idea where that came from, but it's
CYA.
CF, yeah.
Or cover your ass.
That's not what Urban Dictionary says it means. So the main purpose of this chip is when the 2GS came out, they had to be, or it was a goal to be compatible with the 8-bit machine. And there was a lot of legacy hardware that required things to run at certain speeds, and they had to duplicate the circuitry. They wanted to run faster, so there's almost two machines. It's like 1/2, maybe. And so this chip, the FPI, I'll call both versions FPI, is what synchronizes the two sides, and it basically controls the interactions between the two. So it has three main duties that I could find. One, it creates the clock for the main CPU. Two, it interfaces with the fast side of the RAM and the ROM, and it controls access to the slow bus. And then three is it controls shadowing, which is a kind of a feature hack that they created. A lot of these things in the 2GS are like that they created to speed up some older Apple II programs. Right. And they're all interrelated. So I might talk about a term, talking about one of the first things, and mention it in passing, and then we'll get back to it later because they're kind of all joined. So if you have a question, ask it right away, and it's just your responsibility to remember what I was talking about so that I can pick up when I'm done answering questions. So the first thing is the clock generation. And first of all, does anybody know the timing on the 8-bit apples? Or you want a refresher on that? Because I have.
It runs at a megahertz.
Right.
A couple of pulses.
Well, this picture's going to be scary, so don't be alarmed here.
Yeah, it looks familiar.
It looks familiar. I think it looks beautiful. This is this should go on a T-shirt right here.
Yes.
This is all the time signals that are 8-bit, except for the last one.
Stretch?
Yeah, stretch is a 2GS specific signal.
And, okay. Right.
So a lot of them, I guess we don't have to worry about. I drew a lot of these pictures. I drew to be complete, so I'll point out parts that are applicable. The main clock is what drives everything. And for, I guess, the purpose of this discussion, we have phase 1 and phase 2, which are the main CPU clocks. We have all these intermediate things that are used to calculate everything else. But this one, if you count, there's 14 of these in every cycle of these two phases, and these will control the CPU and in most of the processing. You notice these are twice as fast, but they are spread out kind of strangely.
Like a drum beat or a heartbeat.
Yeah, and these are kind of like shifted. You know, one happens a little bit after another because there's a sequence of events that happen every cycle in the 8-bit Apple IIs. And so these two green bars are regular cycles. Every once in a while, every line on the screen, in fact, one of them is a little longer, and that's called stretch cycle. And I don't know how important it is to say why they do that, but it makes the colors easier on the 8-bit too. So you don't have to, like it isn't hard enough to write high-res graphics routine. It makes it, if they didn't do that, it would make it even harder because the colors would be different on even different lines. So this is the older clock, and this is in another chip called the Mega 2, and it's always running. So that's the way they work the Apple II, 2GS, is they basically have the Apple IIe on a chip, which is another chip that I didn't study as much now, called the Mega 2. And so it's always running, and they have the FPI, which is what I am talking about, that controls everything else, and sometimes runs fast, and sometimes doesn't. And when it runs slow, it has to run at this speed. It's to slow itself down here. When it runs fast, well, it would be nice if it could just run fast, but in fact it runs like 3 different kinds of fast. So, yeah.
Any of this connected to the phenomenon one sees sometimes with the 2GS, you've got things occurring in sort of violet and green and white.
This is kind of related. In fact, like this one here, CREF, this is the same frequency that a television uses for the color reference. And it was chosen specifically in TV so that it would not interfere with the regular signal. But in fact, on the Apple II, it's synchronized to the regular signal, and it, like all the color is basically generated by interference. So yes, it's a way that the color is all generated by tricking the TV into believing that just the standard pixels on or off are brightness as well as color information. So this is the slow stuff, and you notice here, this is where the cycle is actually larger, but we have the signal over here. That's, I don't know why I did that, but I'll talk about it. Now we got the fast one, and this one looks a lot better. I think. At least a lot fewer things to do. And
okay.
So these are the two like old signals, the Apple II 8-bit things, and these are all like one clock now. We got some fancy stripes this time, and now this is the fast one, and we have basically 3 kinds of fast clocks. The bottom one is just a variant of the third one, and so the idea is you want to run as fast as possible, but no faster, and so the fastest that the 2GS will run is like 5 of these 14M cycles. So it's quite a bit faster than this. This is 14, we got 5, so that's where you get your 2.8 megahertz on the 2GS if you do the numbers. That's not quite 14, but every one of those bars is like 70 nanoseconds or something like that. And one difference, though, in the 2GS is that whereas in the 8-bit machines, everything happens automatically. Like the access to the video RAM happens to refresh the video RAM, and it has to be refreshed, every so often, or else it forgets. And that's not done in the 2GS. I don't know why they chose not to do it, but probably so. Most of the time, you don't need it, so you can have these fast cycles.
I don't mean to interrupt you. Do you know why they stretched phase 0?
Why this one was stretched? Yes, the reason is, this extra time is half of a color reference.
Oh, okay.
And so one line on the 8-bit Apple IIs is 65 normal cycles.
Right.
there's an odd number of color reference cycles in one phase 0.
Yeah.
So on every other line, the color reference would be opposite. So the color
Didn't look right.
the colors would be different, would be inverted on every other line. So if you stretch one out, just half a cycle at the end of the line, now we're back on, and every line is the same color.
Okay. Wow.
And this one of the reasons now, if there's so many different numbers, like how fast does the Apple II run? Is it 1.024 megahertz? Well, that most of them do run that fast, but every now and again you have ones a little bit slower, and so if you average them out, it's some other number. The 2GS has that thing as well now, because it doesn't refresh its memory all the time. Every now and again, it adds a longer one, and it will do. I think it does the refresh first, and then it does the regular access here. This is why people can't agree on how fast the 2GS runs. You see 2.8, sometimes you see 2.5. I have another measurement maybe I can show on the real machine. Let's see. Yeah. I mean, you can see a kind of pattern here. Here's phase 2. And you see every now and again it's there's a little bump here because it takes a little longer. This is the refresh hit here. And on this trace, it happens, I think, every 9th one. And then the last thing, finally, is when you're really slowing down the whole system. And this is exactly the same width as phase 0, right here, the sync cycle. But it's not the same signal. You can see that all the phase 2 ones, they start out low for 2 cycles.
Yes.
And then they just stretch out the last portion as long as possible. That's how the FPI does its work. If it has to slow down the main clock for any reason, that's how it does it. It just holds the clock on the CPU high for as long as possible to synchronize.
Huh.
And if it has to, I mean, it remembers if the next one's going to be sync, or this one is a sync cycle, and it might have to add a 2. That's why these are almost the same thing, because it might be syncing to one of those longer cycles. Whew. That's a lot. I mean, but these are the main kind of cycles that it has. Now the weird part is the FPI is synchronizing to this phase 0 clock. And I drew another scale picture. Don't be alarmed here. I went through the schematics of the ROM 3 and 1, and I made, this is better than the schematic. And this is all of the clocks only in the machine. And so this is how the 2GS hierarchy is. And they got twice the Apple II speed, 28 megahertz, and that goes into this VGC, which is a video chip. And I don't know what happens there yet. I'll probably do that eventually. And
They use a fast clock, and then they have something that they can divide down at that point.
yeah, the video chip needs it because super high res, I think, has faster pixels.
Yes.
I mean, I know in general, but the video chip does some strange things with it as well. Everything in 2 is strange. But out of the video chip, you get your standard 14M, and that's how
That's just divided in half.
yeah, and that's what the 8-bit chip or the 8-bit Apple IIs. And now a lot of these down here, I wanted to be complete with all these diagrams, like I said, but like the top half is what is kind of important for this discussion, and that this is the video chip, this is the Mega 2, which is the Apple IIe on a chip, and then this is the FPI, which is what I'm talking about. So the video chip gives you this 14M, and it gives it to the Mega 2 and the FPI. The FPI gets the fast clock here to the CPU. And the FPI or the Mega 2 is the Apple IIe on a chip, and it has all the 8-bit signals. It has phase 0, and the FPI never gets it. So it's synchronizing to this clock that it's not connected to. I don't know why.
Did you say what MPI earlier? Did you say what FPI stood for?
Fast Processor Interface.
Okay. Sorry.
You're welcome. Yeah, so it's not connected, but it does have this signal called stretch. And the video chip is connected to phase 0. And based on phase 0, it calculates the stretch signal. This is something new, I guess, it's not documented. So if we go back to what I call the 8-bit stuff, now this extra stretch signal, you can see why the stretch cycle actually happens here. The video chip is just kind of reacting to it, and it does this later, after, like the first non-stretch cycle after. And this is what the FPI synchronizes to. And it must like duplicate a lot of this internally and have its own copy of phase 0. And that's what it synchronizes to. And I've noticed in general the 2GS has a lot of this kind of duplication. They thought it would be nice, to make it 2D on a chip. And then they thought, well, you know what, we actually need these signals somewhere else. So they implemented the same register in another chip and things like that. So this is not the only case of it. Something like this happening. So the FPI, it has its own counter, and this is what it synchronizes to. So that's how it does these, and then the cycle comparison. Right, so that's how it knows which cycle is coming up and how long to wait. That's a lot. Everybody's still waiting. That's why I had to ask on the mailing list if anybody would come. It's a pretty technical thing. The detail is very important. Okay. Now, I guess I'm going to talk about when are these required. This is required, and I haven't figured out if you're running how often a RAM refresh is required. I think it has its own counter, like time-wise, and if after a certain amount of time has elapsed, it decides at the next one. And it's like a window. It's not a set number. So sometimes, like in that trace I showed, I think it was every 9th cycle. But if you have some of these slow cycles mixed in, it might not be every 9. So I haven't figured out exactly when it does that. But why it synchronizes, that it does the sync cycles, that's mostly documented. So, and verified by me, I guess. When you want to synchronize to the slow side. And let's see what I'm about. I guess I list them and maybe talk about them, because some of them relate to other features that the FPI does. Obviously, in the 2GS, you can set the system speed to normal. And then every cycle is one of these. There's another feature on the 2GS that if you're accessing a disk drive in slots 4 through 7, it will detect, the FPI detects that the motor's on, and when the drive's enabled, meaning that the motor's on, then it slows down everything, because the way the disk driver works is it's all very timing critical. The instructions have to run at the correct speed. So that's another reason. Firmware actually scans for disk 2 controllers and all the slots. Well, it does all slots. But 4 through 7 enables this feature if it finds disk 2 card there. And then the next 3 options are kind of related to other topics. One is that if you're writing into video memory, any memory that, not just old video modes, any video mode, like high res, if you run into the high res is at 2000 through 3 FFF. If you write address there, in certain cases, it slows down, and I'll talk about why it does that. And also, any I/O access, like if you're accessing a slot or the serial port, which on the 2GS is on the board, it still counts as I/O, an internal I/O, I guess. And then I talked about the Mega 2, that Apple II chip. It has its own memory on the 2GS, and if you access those banks directly, you get another slot. So, like 5 reasons. I guess system speed is easier. Everybody knows in the control panel. Just you can set that. I mean, this 2 The other ones relate to something else called shadowing, and I guess that's the next part of the talk. Do you know?
952.
Okay, so it's like, okay, that's good. That's good. One of the features that designers of Apple II did is they wanted to make, since they wanted to speed up even existing software, they wanted to minimize the number of times they had to do this. And part of the problem with doing that is if you go back to all the 8-bit clocks, a lot of these, which are like system clocks, are also intertwined with the way that video works. And it was an amazing thing that, you know, we could have this one set of chips that does RAM refresh, it does video generation, it does, you know, actual processing. But now you can't take them apart. And so you had a lot of these things still have to be, you know, are still left over in the 2GS. And even though we have now super high-res graphics, it still uses some of the same scanning circuitry. And I guess the base point of this is that all of the video stuff runs at the slow speed. It's on the slow side of the machine, even the super high-res. So when you want to access video, you have to slow down the whole machine. So if you want to talk about graphics capability and you have speed, you know, if you're a fancy new Apple IIgs, and every time you want access, you know, the thing slows down to the old speed.
So you need super high res, you have to slow down.
Yes, when you access video memory. So they have a kind of feature in that instead of making the first two banks of the processor, which are like the old Apple IIe, you know, main auxiliary banks, they put those somewhere else. And if you want to know, it's like E0 and E1. So they stick them somewhere else. And if you access those banks directly, everything's slow. But now, most Apple II 8-bit software wants banks 0 and 1, which is the only banks that it knows. I mean, it doesn't even know the concept of more than 64K of memory. And so they kind of faked it. If you set up this feature shadowing, and you write to one of the addresses that is shadowed in the lower banks, the FPI will copy it for you. So it writes to both sections of memory. So you get, so it's a slow cycle. I got my other diagram. Yeah, if you look at my presentation. GV. So it's a slow cycle, and but since you're writing it to both, the fast and the slow RAM, you only have to do the writes that way. And you only have to do video memory. Not all of the memory needs to be shadowed. And so when you read it, it's not a slow cycle, and you get a fast cycle, and it speeds up the whole program. So even just running, you know, in Apple II, like if you're running 8-bit game on the 2GS, depending on how much writing it does to video memory, even a fast one on GS, it might be slow just because it writes, you know, video memory all the time, or, you know. So even 8-bit software will run faster if it doesn't access video, things like that. Where am I going with this? I have another one. Now, like this is documented because this is programmer. I mean, the programmer has to know about this, so this is in a lot of the reference manuals. But I think the diagrams aren't that good. They have like a memory map, and then they show like, okay, let's draw this kind of line to represent this range, and they have like 4 or 5 different kinds of lines on top of each other. So this one, I tried to at least spread it out a little. These are just the different kinds of memory. Like these are all the video pages. You have your 2 banks of fast memory, and these are all the little pieces. And for each color, you can turn that on or off, whether or not you want to shadow. I guess if you're running 8-bit, usually I think you just turn them all on. I'm not really sure how the software is used. Other people know that more than I do. One thing to remember, which David Schmink mentioned this problem yesterday in his talk, is this text 2 here. This is another bit in the register. In the round one, they forgot about it. They said nobody used, or nobody thought anybody used text page 2, or they just forgot about it. So, yeah, if you write 8-bit software that uses page 2 of text, which also is space for low res, it won't get shadowed. You'll write it only to the fast memory, and you'll never see it on the screen. So they put a kind of hack in. If you go to the control panel, that alternate display mode, that like when you got your 2GS, you clicked on, or you went to that control panel, and it said it's turning on, it's turning off, and I don't see anything. I don't know what it's doing. That's what it's doing. There's an interrupt, and it copies that page from the fast side to the slow side with software, just to make it work at all. But in the round 3, they do it. So there's still the control panel, but there's another bit in this register that controls shadowing, and now they just flip that bit instead of doing the copy.
But the round one doesn't even have that bit.
It doesn't have that bit at all, but the alternate display mode copies it in software. So if you want to use page, page flipping with low res, you won't.
Is that something they fixed in the round 3 then?
Yeah, there's another bit there. That's why. Otherwise, I wouldn't have this at all. It wouldn't be possible. High res is kind of strange in that because of double high res, you can do page 1 or page 2, or you can just turn off the auxiliary RAM. For high res, you normally only need these ones over here. If it's double high res, you need both halves. So they just have a weird arrangement of how to turn it on and off. And now with 2GS, we have super high res. It has its own bit, and it has a lot more memory. And it only is in one bank, so you can't do page flipping. But like I said, it's still all slow. And that's why even I was going through KansasFest presentation, Chevy did one on how different techniques to write video stuff on 2GS. And a lot of it is just getting the data to the screen fast enough. And there's lots of tricks, to figure out certain instructions, setting up registers like using the stack, or just having a field of basically load immediate instructions that are push immediates because those are faster, and doing it that way. These are all memory, and so they all work the same way, like I said before. They have one other bit they still call shadowing in the Apple IIgs documentation. It's shadowing with I/O, and that's, like I said, read and write. If you access an I/O location in banks 0 or 1, if both the read and writes are shadowed. 1, it could be a register that you're reading. 2 is even soft switches. They don't care what you read or write. A lot of times they just care if you access them, and sometimes the access could be a read, and that flips a switch somewhere. So there's a few exceptions, like there's some registers in the FPI that obviously don't have to be shadowed, they run fast, but for the most part they are. And another little gotcha about this bit, I don't know if everybody's familiar with the way the language card works in the 8-bit Apple IIs. When the Apple II originally came out, we had 48K of memory. In order to get an extra 16K, they switched some memory in on top of the RAM used to be in it. Because the I/O, it has some funny bank switching. Just a lot of hassle to access the memory. But anyways, if you flip this bit and get your I/O, you get that hassle too, of a language card. So it makes the fast RAM act like it has a language card as well. And a funny thing is, normally you only care about the first 2 banks that 2E software can shadow. You can shadow all banks, which means that any 64-byte or 64K boundary in the machine will have this kind of arrangement. And nobody except Ninja Force, I think, actually did that in the mega demo. They set that bit. And I don't know if anybody else actually did that. I think Kegs even has a message. When you set that bit, it says, you must be running the mega demo. I say no, because nobody else does it. But yeah, it could be useful for demos. Okay. Let's do it. And then, so we got Shen. The last thing I talk about is we got. Oh, okay. I got another diagram I took from the schematic, which has more colors. It's like more. Calm down, and we'll go through this. In fact, we'll just ignore anything down here we don't care about, because this is all slot stuff and I/O stuff. But like I said, I want to be complete. These are all different buses in the 2GS. Like we had a diagram for the clocks. These are all the buses, and that's a lot. Yeah, everything has its own separate bus. Like the sound has its own RAM. And you see a lot of these GLU chips in the 2GS, just the interface, and then yeah, there's a lot going on. I guess the main thing for this talk is you have all the fast stuff up here. You have all the slow stuff down here, and there's different kinds of slow, which I don't know if I'll talk about now. But the main thing is you have this buffer here, and the FPI controls that buffer. So anything orange, I think I have like a light orange and a dark orange. This is like the fast address bus. This is the fast data bus. Now here you have the slow address bus and data bus. And the way that the 2GS synchronizes the two is it controls those buffers over there. And so the fast stuff is always just running, and it can actually, in a lot of cases, the buffer is always on. But I guess for a DMA, some of the signals have to go back in the other direction. The way the buffers work is you can turn them on or off, and then you can turn, if they're on, you can say what direction you want to transfer data. And for like the address bus, it's always on, and it's always set to go from the fast to slow. I suspect if you have DMA, it'll change, but I actually do not have a card that does DMA, so if anybody wants to know one, I guess I could take a measurement. But I'm pretty sure that's what it does. And then on the data side, the direction depends on if you're doing a read or write. That makes sense. And whether or not it's enabled always happens with the phase 0 button. And that's another thing I didn't say about Apple II. Another ingenious mad scientist thing of the way that it was. Wrote the original, or designed the original Apple II, is that you notice that the main, the 6502 only really cared about what was in memory during this half. So he says, well, during this other half of the cycle, I'll use that for video to access the RAM. So during the first half, video controls the slow bus. So basically, the FPI turns off the buffer. That's it. Go back. Buses. And all right. So these are always on. It's kind of strange. I think I can show you trace in that. Since they're always on, you don't know if the signals are valid on the slow side. They create some other signal that just tells you if they're good. So sometimes cards might not work in an Apple IIgs that worked in 8-bit because they're decoding addresses at the wrong time. Or so that just the I/O has to know. Because when I was originally studying, I thought, well, it's not going to turn on the buffers unless it's a slow cycle. But it turns them on all the time. And it just tells you when whatever it's spewing out on the slow side is actually good. And you have a lot of these things like this is the RAM has its own bus, because it multiplexes the pins. And it's kind of like the 2E. There's two data buses on the slow side because of the way 2E worked. It's similar to the same thing. And then this is just all the slots. And the sound actually has its own RAM too, which I didn't even look at. It's crazy. Okay. So, I'm going to show now some real measurements here. If anybody wants to see them. It's maybe not as easy. Is it kind of easy to see this?
You can zoom
Okay.
it.
Everyone else sees. Okay. Right, so this is fast. This is, we're doing a program. Let's see what program we did. Oh, okay, this one's easy. So we branched to ourselves. All I did was I took a 2GS and I didn't really connect anything except the keyboard and logic analyzer.
Just an endless loop.
Yeah, yeah. Instead of trying to trigger the analyzer, on some special conditions, I just looped and did the measurement that way. So this is the same thing over and over. You can see here, here's that stretch signal. Zoom in on that. This one is a little longer. It's phase 0 that we're syncing to. Actually, no, that's not right. Well, I mean, it is right because I measured it. I mean, but this one should be after the long one. Maybe if I counted them, maybe come back to that. Yeah. You can only measure with such resolution on the logic analyzer.
Yeah.
So, like if you zoom in real close, I have the 14M, and you notice a lot of them, some like these ones are a little longer on the high side, and it's just because I'm only sampling at certain points.
How fast was your sampling rate?
It was 100 megahertz.
Okay.
So for 14M, you can see, especially like the 28 megahertz clock, looks like garbage on it. As you can see. So I don't know if we can see one cycle. This is related to like the RAM refresh. Maybe you can see we have your 5, and see like all my timing diagrams are ideal. Like if everything happened instantaneously, they're all aligned. That's good for figuring out what like cause and effect. But in reality, you have a delay. It takes a while for something to happen. And so if I see like this marker right here at the start of phase 2, well, this rising edge of 14M is what's triggered, or where it happened.
But there's a delay for it to actually.
Yeah. But if I count like more rising edges, 1, 2, 3, 4, 5, and then somewhere between right at the 5 is the end of this one.
Then it starts to drop.
Here's the 5. And then right here, these are like the RAM signals. And these happen also every 5. Until they don't. And I'll show you a case of that right here. So right here, if is it okay if I show the mouse to you guys? Can you guys pick up on that enough, or can I point?
Yeah.
Okay. So this one from here to here is one of these refresh cycles. So you can see it still is 2 low, and then high for 8. And these signals are in a different order. And the way the RAM works is you give it half the address bits, you give it a clock, this row address. Then you give it the other half, the column address, and then the access happens. Well, every once in a while you have to basically nudge the chip to tell it to remember what it's storing. And you do that by giving it the signals in the other order. So in this refresh cycle, that's what it does. We have the CS first. And I think you only need the CS. You might only need one of these signals, but I think the way it's designed, it always gives you both. You can't just stop this one. I think you only need the RIS, and then you just forget about it the rest of the cycle. So they an FPI, they switch the order. And then the real thing happens here. Real deal. If I zoom out here, this is that special signal that tells you M2 select. And you can see this in the reference manuals. This tells you if you have a slow cycle. And obviously in this case I don't ever. So we're always running faster. But this down here, these are the buffer signals. And this is for the address buffer, these are for the data. And the way they work is here's the enable, here's the direction. Enable, if it's low or 0, which it is, that means it's on. So it's always on, even though we're fast right now. The direction is always high, which means from the fast side to the slow side. And
One way.
yeah, it doesn't change. Like I said, I'm pretty sure in DMA it will change. And here, if I line it up, you can see the data is right on to phase 0, which is kind of strange. Like this, the phase 0 I'm measuring is the real one from Mega 2, and the FPI is using its fake, and you can see they're
They're
locked
right
on.
on line.
So if phase 0 starts off low, right? And so when it's right, so up here when it's low, then buffer is high, so it's off. So it's just like the opposite. It's like
It's opposite signal, so it's like a
it's just inverted. But
yeah.
they don't just really invert phase 0 because otherwise there would be a delay.
Right.
And then so it's on the second. So that's fast. Slow is actually kind of easy because there's really no changes. And this is the same program, just branch back to yourself, definitely. But now in the control panel on mine, actually I think I did encode. Yeah, you have to do encode because in the 2GS, I think if you're in the monitor or something, you go in the control panel and try and change the speed, it puts it back for you. I don't know, I'm trying to be helpful. It wasn't that for me. I wonder there we go. So yeah, there's a bit you flip. That's all this does. It just flips a bit and branch back to this. And by the time I took the measurement, all this stuff was done. So we just have this loop here. Also, once again, also in. Here's now like the first one. We got 1, 2. Now we have all this time where it's high. And I happen to pick one where I didn't actually plan this out. They do a refresh here in the slow cycle. So, and then here's the real axis on this side. If you're running always at normal speed, you don't have to slow down anymore. You're already slow enough to fit in the refresh, so it's always locked on. If you're running at fast speed, then you have to slow down to do a refresh every time. And this is why I can't really figure out yet how often. You can kind of see a pattern now, like of these extra cycles. And one thing too about this M2 select, it's not related to speed, it's different. So we're still running normal speed all the time, but we don't have to access the slow side, so it never goes low. I should say it has to be 0 for it to be on. And the same thing, the address is always on, and enabled, the data is enabled opposite of phase 0. It's always in this direction. Now we get to some interesting stuff. As if my whole talk was not interesting. And I have another loop where we're just reading and storing an I/O location. And I wanted to avoid doing shadowing, so I use it directly in the slow bank. I use the long absolute addressing, and this is, I think, low res. Right?
Yes.
And
Well, it won't do anything if we're not practicing.
yes, yeah, whatever. But
But I still think it's an I/O address.
it's an I/O. It's a valid I/O address, I guess, for one. And I think it really extra reason writes. Well, that's not important to the way the 2GS works. But I want to show you both types of cycles. So we just load, and then we store that same address, then we branch back to ourselves. or at the beginning of the loop. And I should mention, we're in fast mode. Should I do slow first? No. Wow. Now we got a little more to deal with. This is where my leading goes. So don't feel bad, because I had to study this myself. I did these a couple weeks ago, and on purpose I did not look at them, so I would not get nervous. So we have some pattern that you can devise here. And we have some fast cycles, and then we have a slow cycle. So I'm trying to gather, like right here, phase 2. This is the main CPU clock. This one just never studied. Yes?
How does that change? That's phase 2 is changing?
Phase 2 is right, because now I'm accessing the I/O. And whenever I have to access
Oh,
the
it
I/O,
slows it down. Okay.
Now
Yeah,
it
you're in
slows down.
fast mode. Okay. So it slows down to access the I/O. Okay.
Yeah. And so you can tell which one is which somehow. So I also have this signal. This is the read-write signal.
I have no idea. It slows it down like.
Just bizarre to see phase 2 clock.
Yeah. Yeah, and somebody even mentioned the CPU has a feature like to pause a cycle, and they were in, I think it was in A2 chat, IOC, and they were wondering, well, how come it doesn't use that? Well, the CPU can only pause in the phase 2 cycles, which it has. So we're kind of like changing phase 2 itself, so that way it won't work. It's called, I think, a ready signal, which still technically works on the 2GS. I don't know if any cars use it. So this one here, because this is the read-write signal, which I didn't even talk about when I gave me, but this means it's the write. So this is a store, and this is the read. So you can see here, it actually starts. Oh, I know. I give myself some hints here. The CPU gives you these 2 bits that tell you what it's doing. So I don't remember what this stands for, but they tell you if it's reading an opcode, accessing a program, or if it's actually like the address of an opcode, or if it's actually accessing data. And oh boy, now. So we're going to do a read and a write. So you can see that. You guys want to go like cycle by cycle? A load A instruction, it has 4 bytes, right? So you got to load 4 bytes. The opcode is the first byte, and the address is 3. So here we go. This is the first phase 2. This is the first phase 2. These 2 are high, which means we get the opcode. We're reading. CPU read write. It's a high for read and low for write. This is reading the opcode. Then this one goes low, which means now we get the 3 bytes of the address. So this is like the first 4 cycles of instruction. Now we actually have to access the I/O, and on the address bus is the I/O location. And here, sometime in here, and it's kind of weird, like the CPU puts this address out right away, and in this 2 cycles, that where the clock is low, the FPI decides what it's going to do. So it doesn't even know until here. It analyzes the address during this 2, and then it decides to slow down. And that's why we don't see the select until a little later. Because now it's decided, oh, hey, we're going to slow down. And then this is where the read happens now. The phase 2 is slowed down, stretch to here. We do the same thing for the write. We go opcode, we do the same address we had before with these 3, and it slows down. And then you see the read-write is low, which means now we're writing back. So I did a read and write. They're both shadowed. They're both slow now. So we slow it because you see in phase 2 it slows down. And 2 select is on, which means we're accessing the slow side. And then this one here tells you if we're reading or writing. In this case, we're writing. And they snuck in a refresh here too, just for as measure. Because now it's not going on, right? Yeah. Okay.
Is it the FPI that figures out when it's going to do a refresh?
Yes. Yep. Because this is the fast RAM. The Mega 2 controls the all slow RAM, and you know how the video generators actually automatically refresh. That's still going on all the time. The FPI does not control the RAM, the slow RAM itself. It just tells the address to the Mega 2. Another funny thing I told you about duplication before, it's hard to tell. How are we doing time? 10 minutes. Okay. It's hard to tell what piece of RAM or what RAM you're actually accessing, because there's all these soft switches that remap other banks, and change if you're going to main and aux banks. And the FBI has those internally, because if you turn on I/O shadowing, it has to duplicate them. But then it just sends the regular address to the Mega 2, and it does them all again. And it, does the same thing for its RAM address. And the last one, which I think is not as exciting, but it's a read. It's the same loop as before, except we're always slow. This 36 of these is slow. And so phase 2, we got this.
So long, phase 2. So
Yeah, it looks
every one of them.
different. And you can kind of see now the axis is here. Here's the read, the slow read. This is what I want to show. So they're all slow, but you don't need to access the slow bus all the time. So the FBI only enables it when you actually are. These addresses are all valid because they're all synchronized at this time to the slow side, but it still doesn't set the signal unless it has to. I guess that's what I'm trying to show with this one. And one thing I figured out too, it's got some glitches on the signals when it does that. I don't think that's my measurement stuff. So the way it switches is like this little thing here.
Can you bring that in? Can you zoom that in?
Oh yeah. So this is the direction bit of the data buffer, and right when the Mega 2 select signal goes inactive, when the slow cycle's done, I see some glitch.
Yeah, a little glitch in there.
And it's on the fast one too. I just didn't have time to tell you about it. Here it is here. So yeah, I guess chat board, the way it switches, it's not required to be valid then, so it's perfectly fine. It's just the logic, whatever logic they use to decode it, it has an intermediate state before it settles.
For a brief second, it triggers it.
Yeah. So I don't think it's a big deal because I'm too. But they do have a note, in one of those tech notes with 2GS saying, regarding this signal and to select about you shouldn't turn on, because this means if you're reading, if the CPU is reading, that means the card is allowed to drive the bus, and they give recommendations on, do it a little bit after this signal because it give time for the buffer to settle, and then do this one as quickly as possible to turn off, So they give you recommendations on that. Wow, that's a lot of talking. I really have no more stuff, no more things to talk about. I think you're happy about this, except I drew this cool picture of a 2GS.
Very cool. Nice.
Are there any additional questions?
So kind of unrelated, but what OS are you running on that laptop?
It's Linux.
What distro?
I just compile stuff.
Oh, okay.
In the 2GS question.
Just in very broad terms, do you know what accelerators do?
I do. Imagine another set of buses up here. That's what it does.
Okay. All right.
It does the same kind
another
of thing.
buffer, another FBI.
Because what the CPU or the accelerator has its own clock, and it's running as as fast as it wants to, and moving ever so slightly. And so you take out the CPU usually, and you have a ribbon cable. I don't think there's any 2GS accelerators that don't do that. That's it. Transfer only two. They both have a card and a ribbon cable which replaces the CPU. And so they had to synchronize to the phase 2 now. which may have all these variations, and they have their own fast clock, and it's a lot harder even, because in all the diagrams that I showed, at least there's one big clock at the top that everything is derived from. So everything's synchronous to some degree. An accelerator, you notice, all the overclock is, you have another crystal that you put in, and it's running at its own rate. And so there's other problems about, you have to be sure what data is valid and things like that. And so they do this whole thing all over again. They do a little more in that the FPI, the way Apple chose to do the synchronization is whenever you have to access the slow side, just make this part that slow. Access it, and then you're done, and then run fast again. In the accelerators, they didn't want to do that as much because the RAM is that slow. You usually access it. In fact, 65 series all accesses RAM every cycle. So they have some additional caching where they'll cache, they'll remember what they wrote, and I haven't studied that too much. But yeah, they have an additional layer of complexity on top of just the clock stuff, just the memory stuff. I don't know the Apple II 8-bit stuff, if they did caching or not, if they just ran, I think just ran everything fast. There was so little memory that they could do that. The GS has the option for more memories. Oh, right, another reason I didn't do it is because the whole reason I started doing this stuff is I really didn't care about that. And the reason why is I wanted to try and duplicate the 2GS in simulation. And let's see. Oh, right. So I started trying to duplicate the FPI in my Rogan barrel log. And so I want to make like a faster 2GS. But instead of doing an accelerator, I'm just basically cloning the FPI. And so right now I have some stuff here, like all the 8-bit signals. I think that looks great, doesn't it? It has a little stress signal there. But yeah, so I figure if you're going to duplicate the FPI and not even go the accelerator route, then another way of making things faster, I mean, the most obvious way is maybe just make this down low one and up high, things like so. That was my approach to speeding up the 2GS experimenting with that. So I guess if you want, I guess this is an official announcement of when I'm working on this project. So yeah, I'm trying to clone 2GS eventually on an FPGA, and I didn't want to say anything before because it's a lot of work. But I actually have the one thing that I guess was hard that nobody had before is the CPU core, and I have one that's pretty much complete. So if anybody does FPGA stuff and wants to help, maybe we can talk afterwards. And I have FPIs half in progress. That's all I have so far. But I figured CPU, at least in complexity, is as much as all the other chips on the machine. Probably not in his documentation-wise, though, so it's still a lot of work just figuring out what everything does. Whereas it might not be that complicated, we just don't know what it is. Any more questions? Got time?
You don't have to have any photos in your test group, do you?
I didn't think about that. Well, I did think about it, and I should have on camera. So I do not. Maybe I can post them. I know they always have the notes up on the KansasFest site. I can do that, yeah. I'm not sure.
So use paintbrush, draw a stick figure yourself. I was on that before.
Yeah.
Ask here.
Yeah. Oh, yeah, I get this too. Cool. I didn't know what day I was going to do it on, so that's why I didn't do that. Yeah, so the CPU I got running. A lot more signals to deal with. These are all internal signals. I can scroll out and see some stuff happening. like on a cycle-by-cycle basis, what output is running. All right. I think that. Anything else? Yeah. Yes, sir.
Yeah, after you've been studying this so intensely for the last bit of time, in your opinion, did they go the right route redesigning the 2GS in this direction? Or do you think there's something they should have gone in instead?
Well, the right route, I mean, it's the 2GS in general is kind of, you can look at it two ways. It's kind of amazing that it works at all. But a lot of things it's like clever how they make things work. I mean, I'm not sure how else you could do it. If you wanted to keep compatibility, which was one of their goals with the 8-bit machines, not just on a software, but on an interface card level, I don't know. I mean, this was pretty, I don't know, straightforward, but I mean, I can see why they chose to do things this way. I haven't thought about, like, if I was doing it, how would I do it? I mean, I kind of am, but I'm taking their general approach and just making, tweaking it, like adding a clock on some other appliance and selling it as something new and improved. That I don't know how else I can do it, but yeah, it's that kind of awe and disgust. That's again when looking at this design.
How long have you been working on this?
The coding or
Just
the
the
whole
timing
thing?
signals and study all in general.
Maybe December. I took a couple of months break for other things. Yeah, this coding took a while.